For our dipole example now, what we'll do is let's draw the electric field lines around a dipole. So here's our positive and negative charges separated by a small distance d. That makes them a dipole. We're going to draw the electric field lines. We're going to draw the net electric field at points A, B, and C. And then to finish, we're going to calculate the electric field at point A. So when we draw electric field lines, we have to remember that electric field lines go out of a positive and into a negative. And then we also remember that the number of electric field lines is proportional to the size of the charge. This charge is plus Q. This charge is minus Q. They have the same magnitude of charge, so the same number of electric field lines will go in and out of each. Okay, let's draw our first line out of the positive and in towards the negative. Then we'll draw another line and another line and so on. So all of our electric field lines that start on our positive will come around and finish on our negative. That's more or less what the electric field lines look like. Then if you wish, you can compare what we just drew, this picture, to what we might find on a PhET simulation. So if you Google PhET, P-H-E-T, electric fields, you'll come to this simulation. Then if you draw the electric field, you see that it just follows the lines provided. So what the PhET simulation shows us is the same as what we drew. So next, let's draw the net electric field at point A. So the electric field at point A has a contribution due to a positive charge. It has a contribution due to the negative charge, and the total electric field would be the vector sum of those two. The electric field due to the positive charge will point away from the positive. We put our pen on point A, and then we draw a line that goes away. There's the electric field due to the positive. For our electric field due to the negative, we put our pen on point A, we go toward the negative, and we might also think about the relative magnitude. The negative charge is farther away than the positive charge. It means that the electric field due to the negative charge is going to be smaller. So to draw that electric field, we put our pen on point A and we go towards the negative charge. There's E from the negative charge. Okay, the net electric field will be the vector sum of these two. So we have a long vector up, a short vector down. The net vector would be a shorter vector up. So the net electric field points up. Then if you wish, we can compare that with a PhET simulation. So our PhET simulation shows that the net electric field at some point above the positive is straight up, and that matches what we drew on the previous slide. For our net electric field at point B, we'll first draw the electric field due to the positive charge. We put our pen on point B and we go away from the positive. So there's our electric field due to point B. For our electric field due to the negative charge, we'll put our pen on point B and we'll go towards the negative. Our negative charge is farther away, so the vector is going to be smaller. So it looks something like this. For our net electric field, we have to do the vector sum. This one is big and all to the right. This one is small, partly left and partly down. So our net electric field vector will have a component that points down and a component that points right, but it won't be quite as long as the positive vector was. So our net electric field vector will look something like this. We can go ahead and compare that to a PhET simulation if we wish. So our PhET simulation confirms what we found. The total electric field directly across from the positive charge is towards the right and down. Last, we'll draw the electric field vector at point C. For electric field due to our positive charge, we'll put our pen on point C and then we know we go away from the positive. So it's going to look like this. Electric field due to the positive. For our negative charge, we know that we have to put our pen on top of point C and go toward a negative. The positive and negative charges are exactly the same distance from point C, so the vectors are going to be exactly the same length. Because our vectors are the same length here and they're at the same angle due to symmetry, the x components are going to cancel and the y components are going to add up. That means our net electric field vector is going to point straight down, a bigger y component than either of them. We can also take that vector and compare it against a PhET simulation. So again, our PhET simulation confirms what we drew in our picture. The electric field at point C, which is midway between the two and to the right of, that electric field net vector points straight down. Let's get to work at finding an expression for the net electric field at point A. So we know how to draw it. We know that the electric field due to the positive charge points straight up. We'll call that E plus. We know that the electric field due to the negative charge points straight down. We'll call that E minus. And we know that the net electric field at point A is the vector sum of E plus and E minus. Okay, next, why don't we put in a coordinate system? Let's say that positive y points up, positive x points to the right. We need an origin, so I'm going to put an origin right at the center between those two charges, midway. So this is y equals 0. That means that our point A is some distance y above the origin. So from here to here is y. Okay, super. Now we've got our coordinate system on there. Let's think about our vectors just a tiny bit more. Our electric field due to the positive charge points straight up. So E plus is positive, has a magnitude of E plus, and is in the j hat direction. So the y component of our positive charge is equal to plus E plus, positive E plus. Okay, for our negative charge, that points down, so it's negative, with a magnitude of E minus, also in the y direction. So the y component of the electric field due to that negative charge is negative E negative. Okay, so if we want to find the net electric field, we know that that's going to be a y component because we don't have any x's going on. So the y component of the total electric field is E plus the magnitude, subtract E minus the magnitude. So we find the magnitudes of those two electric fields and we just subtract them. So how to find the magnitude of an electric field? We remember that electric field is K times the charge divided by R squared. That gives us the magnitude. K is equal to Coulomb's constant, 8.99 times 10 to the 9 newtons meters squared over coulombs squared. Okay, so in terms of the charges we have, E plus is K times our magnitude of our positive charge Q divided by the distance between point A and our positive charge. I'm going to call that R plus. Subtract K times the magnitude of our negative charge, which is Q, divided by R minus. Oh, dropped my squareds. KQ over R squared. Okay, let's get R plus and R minus on our diagram. R plus is the distance between our positive charge and point A. There's R plus. Let's get R minus on our diagram. That's the distance between our negative charge and point A. So this is R minus. We'd like to find our electric field at point A, which is some distance y from the midpoint. So let's think about how are we going to relate R plus and R minus and this y value. Well, it seems to be related to the distance between the two charges. The distance between the charges is d. We took our origin as at the midpoint. So from the positive to the middle is d over 2. And from the negative to the middle is d over 2. Okay, let's put all that together. R plus, the distance between A and our positive charge. This distance right here, we see that R plus d over 2 equals y. So this whole distance here can be written in two ways, R plus d over 2, or it can be written as y. So that means that R plus is equal to y, take away d over 2. And that's our distance between the positive charge and point A. For the negative charge and point A, that's this distance right here. Two ways to write that distance. We can write that as either R minus or y plus d over 2. So between here and here is either y plus d over 2 or R minus. So r minus is equal to y plus d over 2. So now we've got our distance in terms of the separation between the two charges and where we're trying to calculate the field. Let's fill in those expressions for our electric field. So we've got k times q over y minus d over 2 squared minus k times q over y plus d over 2 squared. Okay, now we've got to figure some stuff out. This is a little bit of a tough calculation to do. Let's apply some thoughts and let's remember that this distance d is very small, and let's see if we can get a simpler expression for y minus d over 2 squared. So let's get going on figuring this out, and let's focus in on this term first. So 1 over y minus d over 2 squared is equal to 1 over, I'm going to do a trick my first year math prof told me, which is that you can always multiply by 1. So I'm going to take my d over 2 and multiply it by y over y. So now what I see is I've got a y in the numerator here, y in the numerator here. I can take those outside my brackets. So this is equal to 1 over y outside of 1 minus d over 2y. And this whole thing has to be squared. Okay, so since the whole thing is squared, that means that the y is squared. So I've got 1 over y squared times 1 minus d over 2y squared. So that squares both terms. This is the next term I need to focus on. So now this is equal to 1 over y squared times 1 over 1 minus d over 2y squared. So our next step will be, let's figure out what this bit is. Okay, now let's get to work on this term. So 1 over 1 minus d over 2y all squared. Got two terms in the denominator, so we just have to multiply those out. So that's 1 minus d over 2y times 1 minus d over 2y, because that's what squared is. Okay, so we've got to multiply those four terms out together. That's going to give us 1 over 1 times 1 is 1. And then we've got minus d over 2y minus d over 2y plus d squared over 4y squared. So I just multiplied out each of those terms. In high school, maybe they called that the FOIL method or something. So these two, they're going to add up to give us minus d over y. And then for this term, this one's a little bit interesting. Our starting premise is that our distance between the two charges is very small. That means that y is a lot bigger than d. That means that d squared over 4y squared, d is really tiny, and when you square it, it gets even smaller. Y is pretty big, so we've got a tiny numerator divided by a big denominator. This whole term is about equal to 0. So then our expression is approximately equal to 1 over 1 minus d over y. So now that term has simplified a little bit. Still going to be a little bit dicey as we go through our algebra. So let's see if we can do something about this term, and let's see if we can sort this out a bit. So 1 over 1 minus d over y. I'm going to multiply this by 1 again. I think they call this completing the square. I'm not up on my high school math terminology as well as I might be. So in my numerator, I've got 1 plus d over y. In my denominator, I've got 1 times 1 is 1, minus d over y, plus d over y. Multiplying out those inner and outer terms. And then for my last two terms, I've got minus d over y times plus d over y to give me minus, oops, there's a bit to write a plus, minus d squared over y squared. Okay, minus d over y plus d over y, that gives us 0. Once again, we've got d squared is very, very small and y squared is pretty big. This whole term is pretty close to 0 when you compare it to 1. So this expression, this little bit right here, is about equal to 0. So that means our whole term now is about equal to 1 plus d over y divided by 1, which is equal to 1 plus d over y. Okay, now we're going to put all this back together. So why don't we even do a summary on the next slide just to make sure we've got it all clear. So to put it all back together, we said that our net electric field at point A was the vector sum of the electric fields due to the positive and negative charges. We wrote that in terms of their magnitudes, and we remember that the positive electric field pointed up and the one due to the negative charge pointed down. We used E equals KQ over R squared. And it got us an expression for the magnitude of the total electric field. First, we focused in on this value right here, 1 over y minus d over 2 squared. What we found when we looked at that was 1 over y minus d over 2 squared. We found that that term was equal to 1 over y squared. Oh, that looks like a negative sign, but it's not anything, times 1 over 1 minus d over 2y squared. That was the first thing we sorted out. Then we looked at this bit in particular, and what we found about that bit was that 1 over 1 minus d over 2y all squared is equal to approximately 1 plus d over y. So what we'll do is let's put this bit in for this bit, and then we'll put it back together with this bit, and then ultimately we're going to put it back over here. So we're going to put things back together. So 1 over, I meant to change colors there. 1 over y minus d over 2 squared is now approximately equal to 1 over y squared times 1 plus d over y. So that takes care of how we're going to manage this part. We have two parts in our expression. We have a bit over here. So we could apply exactly the same treatment, and what we'd find is that 1 over y plus d over 2 squared, we would find that that's approximately equal to 1 over y squared times 1 minus d over y. So now we have expressions that we can fill into our equation. So let's go ahead and fill those in, and let's work on finding our total electric field. So now we'll fill in what we just found. So our electric field is going to be K times Q outside of 1 over y minus d over 2 squared minus 1 over y plus d over 2 squared. Just take my K and Q outside. That's going to be approximately equal to KQ outside of 1 over y squared times 1 plus d over y. Subtract 1 over y squared times 1 minus d over y. Okay, I want to try and be nice and careful with my brackets here. I don't want to lose track of my plus and minus signs. I'm going to hold my y squared outside because that's in both terms, or in all terms. So I got KQ over y squared, 1 plus d over y, minus 1 plus d over y. Okay, I've got 1 minus 1, that just goes to 0. That gives me k times q over y squared. D over y plus d over y is 2 times d over y. We're close to our answer now. We're going to do a next step of a new definition. So I've written down the expression we just found, and I also simplified our diagram. We've got our plus and our minus charges here. Point A was a distance y away from the midpoint, and our electric field vector pointed straight up. That's because the electric field due to the positive charge was up and big. The electric field due to the negative charge was down and small, so the net vector pointed up. So in writing our final electric field vector, I'm going to introduce a new quantity called the electric dipole moment. So we define P as the electric dipole moment And P has a magnitude of charge, Q, times distance between them. So the units are coulombs times meters. So that's the magnitude of electric dipole moment. Electric dipole moment is a vector, and the direction is from the negative charge towards the positive. So let's see how that works in our expression for our electric field vector EA. So that has magnitude of K times 2 times QD. Y squared times Y gives us Y cubed. Now QD, that's just the dipole moment. So EA equals K times 2 times QD. Oops, Y cubed is Y squared times Y. Oops, oh my goodness, I'm just making a snarl of this. Try again. I've got K times 2, QD is our dipole moment P, and that's divided by Y cubed. Our electric field points up, so I'm going to call that J hat. The direction of from negative towards positive is positive J hat. So P times J hat is our electric dipole moment vector. The electric field at point A could also be written as 2 times K times the dipole moment P divided by Y cubed. Okay, so that's a pretty interesting result. That gives us the electric field at distance A away from the charges, but along the same line connecting them. As a homework question, you might try and find the electric field at point C following a similar method as what we did right here. The last little piece we'll discuss now is what happens when we place a dipole in an external electric field. So we have our dipole, plus Q and minus Q, separated by a small distance d. We're going to place it in an external electric field represented by these arrows. We know that every charge will feel an electric force, F equals QE. So let's find the force on the positive charge and the force on the negative charge, and let's have a look at those forces and see what it tells us. So the force on the positive charge, we'll call that F plus, and it's equal to the charge times the electric field. That force is going to point to the right. Because when charges are positive, the force and the field are in the same direction. For our negative charge, we know that the force and the field are in the opposite direction. So the force on our negative charge is going to point to the left. The force on the negative is equal to minus the magnitude of the charge times the electric field E. Okay, so if those are our forces, we might ask what is the net force? And the net force would be the vector sum of those forces. So that would be QE minus QE equals 0. Okay, what does that mean? Well, that means that the sum of the forces is 0, so the acceleration of the dipole as a whole has to be 0. But you might ask, does the dipole move? All right, so is it going to move? Well, if the positive charge is pushed to the right and the negative charge is pushed to the left, I would argue that this dipole is going to spin. It's going to turn around in this direction. So the top bit goes right, the bottom bit goes left, and it spins in a circle, just like a little DC motor. Okay, so is there motion? The answer to that question is a resounding yes. So if we ask, how can there be rotation because or how can there be motion because the force is 0? Well, we know that there's going to be rotation, and we know that we get rotation when the torque is not 0. So we know that the torque is not going to be 0. So let's see if we can sort out the torque. If we're going to sort out the torque, we need to figure out a pivot point. I'm going to place the pivot at the center between the two dipoles. So this is going to be our pivot. And we know that when we're calculating torque, we need the distance from the pivot and we need the applied force. So the distance between the pivot and the positive charge is going to be a half of the separation, d over 2. The distance between the pivot and the negative charge is also d over 2. So the torque, the magnitude of the torque on the positive charge is our distance between the charge and the pivot times the magnitude of the force, Q times E, times the sine of the angle between the force and the lever. So that angle, extend our line here, that's our angle phi right here. If we were thinking about which way does it spin, if we look at our rotation, this one goes to the right, this one goes to the left, that would be a clockwise rotation. We can put that in brackets at the end. For the torque on our negative charge, that would have our distance to the pivot, and we'll just write down the magnitude first, times the magnitude of the force, times the sine of the angle between the force and the lever arm. That angle again is the same angle phi. So then our net torque, oh, and that also produces clockwise motion. Our net torque would be the two torques added up, which would give us d over 2 QE sine phi plus d over 2 QE sine phi, gives us Q times E times D times sine phi. This is kind of an interesting result. When we look at this result, we see Q and we see D here. So let's ask ourselves what that means. So we've got our expression for the net torque on a dipole. In an electric field E. And if we look at Q and we look at D, we might remember our dipole moment P. So P is equal to Q times D, and that's what we defined as our electric dipole moment. So we could write down that the magnitude of our torque is equal to the dipole moment P times the electric field times the sine of the angle between them. This, you might remember, looks like a cross product. So our result is that the net torque on the dipole is the cross product between the dipole moment and the electric field. So that's a pretty interesting result. If you know something about the charge and the separation in the field, you can find the net torque on it. What this tells us, we might think about, is how do we get the greatest torque? So if we have an electric field that points to the right, like we have above, we'll get the greatest torque, or the greatest torque, the fastest spin, if our dipole is aligned this way. So this is where everything is perpendicular. So this would be greatest torque, rotation. And then if our dipole were lined up with our field, we wouldn't get any rotation at all. So if our dipole were lined up this way, we wouldn't get any rotation or any torque. So the angle between that dipole and the field really matters. It tells us that the torque is going to tend to align a dipole with the net electric field. One last bit we'll add in here before we finish up is that if we wanted to, we could use the fact that work, which is the integral of torque with the angle, we could use that expression to find the potential energy of a dipole. And the potential energy of a dipole would be the dipole moment dotted with the electric field. Your textbook goes through that if you're interested. We don't really cover that bit in the class, but it is there if you want to have a read about it.